Hey, welcome back. In this video, we're going to go over another example on mesh analysis, in this case using a circuit where we have two voltage sources and basically two mesh or two loops that we're going to be working with. So I think the best way to do this is to first just draw on assumed currents through all of the resistors. You're not going to see everyone doing it this way, but I find this is an easy way to not get lost. So it honestly doesn't matter which way you draw them. It helps, you can try to guess, but if you get them wrong, don't worry about it at all. Just go like that. You can even label them on like A, B, and C just to give them some names. But I find this reduces a lot of the confusion in the method. Now the actual method starts now when you basically label on your mesh currents. So we label on a mesh current in each loop. We're going to have I1 and let's call this I2. Generally, it's common to draw them both going clockwise, so we get all of them, like all of the mesh currents, if you have multiple ones, all having the same kind of sense. So what I would do next is relate all of the branch currents to the mesh currents. So if we had IA, IB, and IC, like that, I guess this would technically be IA, IB, and IC. We have to figure out what these are in terms of the mesh currents. So looking at IA here, we're saying that IA is going this way, but if you wanted to draw on our mesh like this, it's going in the same direction. So IA is going to equal I1. So we can write that down here. When we look at IB, IB is going this way through the resistor, but I2 is going the other way. So IB is actually going to be ending up being negative I2, as they have opposite directions, but they'll have the same magnitude. So let's write this on as negative I2. And then for IC, we have I1 going this way, and I2 going this way. So considering that IC is going down, it's going to be the net of I1 and 2. And we're just basically going to have I1 minus I2. So now we're going to do KVL for each loop. So we'll start with the loop number 1 on the left-hand side, I guess. So we'll have KVL loop 1, and let's pick a starting point. Let's just start right here. When we go up into the battery, we're going to go into the negative terminal of the battery, so I'm going to choose that to be a negative sign in the summation. So we're going to start with a -3. And then when we enter into the resistor, we're entering in the positive terminal, so I'll take that as a positive. And resistance, or sorry, the voltage, remember we have Ohm's law, which is V equals IR. So we don't have the actual voltage drop right now, but we do have the resistance and a term for the current. So it's just IA times the resistance, which is 2 ohms. Now I'm just going to drop the units because each term here is going to be basically in units of volts. So we're just going to have 2 IA. And then when we come to the next resistor in the middle here, basically we're going to enter through the positive terminal, so it'll be a positive term. And we have the resistance times the current. So 1 ohm times IC. And that's positive, so we have 1 times IC, and that all sums to 0. This is the extra step that I like to do. You don't have to put IA and IC, but what you basically do have to do is you have to convert these into I1s and I2s, because this is what relates the left-hand side to the right-hand side through this expression for the current, the actual current flowing through IC. And that's how we're going to basically get our 2 unknowns and 2 equations. So we have -3, that doesn't change, plus 2 times IA, but we already determined IA to be equal to I1, so this is where we would write times I1, and then plus 1 times IC, which is just I1 minus I2. So this is I1 minus I2, and that's all equal to 0. Okay, so we can just simplify this a little bit more and get 3I1 minus I2 is equal to I3. So at this point we have 2 unknowns, so we need another equation. So we're going to do KVL around loop 2. And we can start somewhere else. Maybe let's start up in the top middle here. So when we go clockwise around, we're going to first enter this resistor here through the negative terminal. So we'll start with a negative, and it's basically 4 times IB. Then when we come around and enter in the positive terminal of the battery, that's a plus. We have plus 2, and then we're going to come around and enter in the negative terminal of this resistor, so we use a negative sign, and it's 1 ohm times IC, and that's all equal to 0. So now we substitute IB and IC for these I1s and I2s. So we have negative 4 times negative I2 plus 2 minus 1 times IC. So it's minus 1 times IC, and IC is I1 minus I2. That's all equal to 0. There's a whole lot of negative signs in here, and this is why I like to actually draw these on first, because you get really confused. Sometimes if you go with I2, you think, well, like the current is going in this way if you're dealing with substituting I2 first, but really we're substituting the actual branch current, which is IC, and I think it's worth it taking this extra step, figuring out what the relationship is here, and then doing this and then substituting, because it's so easy to get off by a negative sign in here and make a mistake. But either way, we can simplify this, and we're basically going to get I1 is equal to 2 plus 5 I2. So we can take this I1, and we can directly substitute it in right here. So we're just going to get 3 times 2 plus 5 I2 minus I2 is equal to 3. So we can just simplify that. That's just 6 plus 15 I2 minus I2 is equal to 3. Let's give ourselves a little bit more space to work here. But we're basically just going to get 14 I2 is equal to negative 3, and I2 is ultimately equal to negative 3 over 14, or it's equal to negative 0.214. That is in amps. But we can pretty much just take that and then plug it right back into this guy. So we have I1 is equal to 2 plus 5 times negative 0.214. And we find that I1 is equal to 2 minus 1.07. That's I1. And I1 is ultimately equal to positive 0.93 amps. So now we know I1 and I2. If that's what you were asked for in the beginning of the problem, you can just write that and stop here. If you were asked to find the branch currents, or like the currents flowing through each resistor, we can do that as well. Because I1 is just equal to IA, so IA is going to be equal to 0.93 amps. We can label that on the diagram, 0.93 amps. IB is equal to negative I2. So I2 is negative 0.214, so the negative of that is just positive 0.214. So IB is equal to positive 2.14. And just notice that that's, the negative sign just indicates it's going, opposite the direction of I2, which was going the other way through this resistor. And then IC is just equal to I1 minus I2. So I1 is 0.93 minus negative 0.214, which is positive 1.144. So let's label that on here. It's equal to positive 1.144 amps going down through this resistor in the middle. And that checks out as well using Kirchhoffs' current law at the junction, because 0.93 plus 0.214 is 1.144. So yeah, there's another example. If you were asked to find the power dissipations and stuff like that in the resistors, you could as well, but typically the question is often asking you to find either just the mesh currents, so that is the blue ones, or to find the branch currents, the currents through each of the elements, which are written in green. And that's why I like actually labeling them on here and relating them to make sure that you know which one is which, because it can get pretty tricky with negative signs if you lose track. So yeah, hopefully that all makes sense, and join me in the next video and we'll go through an example with 3 mesh loops.